Hello everyone, I'm Norman Wildberger. This is our third famous math problem so far in this series. The last two problems dealt with factorization of large numbers and the Collat's conjecture. Arguably, both of those problems are rather esoteric. Their importance and significance are debatable from the point of view of, say, an engineer or a practical person, because they're rather exotic. They deal with very large numbers, or this rather strange and artificial situation of the Collat's conjecture. Not all of our problems are going to be like this. So some of the problems in this series are going to be very practical and down to earth and historically important. In fact, generally speaking, the older a problem is, the more likely it is to be important. The problem we're going to be talking about today is arguably the most important problem in geometry and has a very illustrious pedigree. So it's the problem of the Apollonius circle constructions. And it was posed by the famous Greek mathematician Apollonius of Perga around 200 years before Christ. Now, Apollonius was one of the greatest mathematicians of the ancient era, and probably following Euclid and Archimedes, he was probably the next most important of the Greek mathematicians. He was almost surely the most famous and important geometer of all time. He wrote an extensive treatise on conic sections, parabolas, ellipses, hyperbolas, in fact gave them their current names. And some of his work has been lost. In particular, his solution to this famous problem was given by him. We know of references to a book called Tangencies where he solves these problems, but we don't actually know how he solved them. Alright, so here's the problem. It says, given three objects in the plane, either a point, which we'll usually denote by capital P, or a line, which we'll denote by capital L, or a circle, denoted by capital C. So given three of those, show how to construct a circle touching each tangentially. So for example, suppose we're given a point P, a line L, and a circle C in the plane. Then our job is to find a circle, in this case, for example, the red one, that, well, first of all, goes through any of the points, and secondly, is tangent to any one of the lines involved. So it's tangent to this line here, and it's also tangent to the circle. So it just touches it at just the one point. So in the ancient Greek world, constructions meant ruler and compass constructions. So you were allowed a straight edge and you were allowed a compass. And so Apollonius would have said, how do you find the center of that circle? That's the central problem. So once you found the center of the circle, in this case, you just open it up so it's touching that point P, and then you rotate your compass around. Now, a bit of thought shows that in this particular configuration, this red circle is not the only solution. So I hope you can see that there's probably another solution, a circle that goes something like this, that also goes through the point P, is tangent to the line L, and is tangent to the circle C. And in fact, there may be other solutions too. Please have a think whether you can see any other solutions to the problem. Alright, so that's the famous Apollonius circle construction problem. And it's a very interesting problem, and it's quite challenging. And I'm not going to show you today how to solve this problem, except in a few special cases. But I am going to leave this problem with you as a challenge. All right? So although this is a solved problem, it's a great problem for aspiring geometers to cut their teeth on. This problem teaches us so much about, not just about circles, but just about geometry and constructions too. So let's have a look in a little more detail at this problem. Contained in Apollonius's challenge, there are actually 10 sub-problems, because we can choose the three objects to be either points, lines, or circles. And I'd like you to think of the 10 possibilities as forming a pyramid. So here's how we're going to think about the various possible sub-problems in Apollonius' challenge. Down at the bottom are the situations where we have only points and lines. So here, PPP, this represents the problem where you have 3 points in the plane and you want to draw a circle through them. This one here, LLL, represents the situation where you have 3 lines in the plane and you want to draw a circle which is tangent to those 3 lines. Then intermediate cases, when you have 2 points and a line and you want to draw a circle that goes through the 2 points and touches the line. Or PLL, you have 2 lines and a point, and you want a circle that goes through the point and touches the 2 lines. Then moving up one layer, we introduce one circle. So point, point, circle, point, line, circle, or line, line, circle. Then one step further, where we have 2 circles, either 2 circles with a point or 2 circles with a line. And for example, with 2 circles and a point, you have these 2 circles and a point, then you have to draw a circle which touches the 2 given circles and goes through the 3rd point. And at the apex of the pyramid is the hardest problem. The problem where the 3 objects are themselves circles. So where you have 3 circles in the plane, for example, this one, and this one. And you must construct a circle which is tangent, touching each of the 3 given circles. For example, this red one would be one possible solution. Okay, so these are all solved problems, so they get a difficulty level between 1 and 5. And in fact, we get the whole spectrum here. The 2 problems here on the end, I will judge them to be D equals 1 problems. They're pretty easy to solve, and I'm going to show you how to solve them. These ones here, maybe D equals 2 problems. They might take you a day of work. With 1 circle, maybe a week of work. With 2 circles, perhaps a month of work, very roughly. And with 3 circles, this is a very challenging problem. And to solve it probably requires on the order of a year of concentrated work, give or take. So it's a very significant problem, and it's a lovely sort of ladder. You can work your way up and try to solve the simpler cases, and then once you've figured out those, try to move up and solve some of the more complicated cases. This problem has been studied and solved by lots of people. So Apollonius I, he posed the problem and also solved it, although we do not know his solution. In particular, we don't know his solution for the 3 circles case. Pappus, who was a later commentator and mathematician around 300 after Christ, he refers to Apollonius's work, and so we know about Apollonius's solution because of Pappus's work. The mathematician Van Roomen in the 16th century gave a construction for the 3 circles case, but it involved hyperbola, so it actually sort of went outside the classical realm of Euclidean ruler and compass constructions. Viète, a famous French mathematician in the 16th century, also one of the very big contributors to algebra. He spent a lot of time thinking about this problem and came up with solutions. Perhaps the most elegant solution to the 3 circles case is the one given by Gergon in the 19th century. It's a synthetic construction problem without any algebra. A lot of other people have thought about this problem and various consequences. Euler, Gauss, Newton, many other people have at some point or another studied this problem. It's a very natural problem. It's a very interesting problem. It comes up in practice. If you're doing geometry and doing a lot of geometrical constructions, you will probably bump into this problem at one point or another. So Apollonius came after the time of Euclid and Archimedes, and he was certainly influenced and would have been familiar with the work of Euclid and Archimedes. Euclid actually solved 2 special cases of Apollonius's problem. The first one is the PPP case, where we have 3 points in the plane, and it's a very familiar and important problem. How do you construct the circle that goes through those 3 points? Well, hopefully most high school students know how to do this, although that's questionable these days because people don't get enough geometry, even very elementary geometry, in school anymore. Very sad and remarkable situation, and one that ought to be changed. Okay, so how does Euclid teach us how to do this? Well, the idea is to construct the 3 perpendicular bisectors of the 3 sides of this triangle. Perpendicular bisectors are lines which are perpendicular to the sides of the triangle and go through the midpoints of them. I like to call these lines also midlines, a little bit shorter than perpendicular bisectors. So here the triangle ABC, our original 3 points, and here you've seen the 3 perpendicular bisectors. The perpendicular bisector of this side is this line here, the perpendicular bisector of this side is this line here, and the perpendicular bisector of this side here is this line here. And those 3 lines meet in a point, call it O. And that's the center of the circle that passes through the 3 points. And that's a purely ruler and compass construction because Euclid teaches us how to, for example, construct a perpendicular bisector. This is a very easy thing. So suppose we have this line here on the side AB, and we want to construct this line with a ruler and compass. So what we do is we open up our compass. Here's a compass. Okay, so it's this device, I hope you've seen it. It has a sort of pointy arm that sticks onto the page at some point, and then you swivel this around this arm. There's a pencil or pen here or something to draw, and as you swivel it around, it will draw a circle centered at that point there. Alright, so if you put your compass so that it's centered here, and say going through this point here, then you can draw a circle. So I'm not drawing that whole circle here, but I'm just drawing part of it, namely that little arc of it and that little arc of it there. And then you lift up the compass and center it here and draw a circle through the other point, and then you get another circle that looks like this. And it has little arcs here and here, so it meets the first circle in these 2 points. It's not hard to see that these 2 points then are the generators of this midline or perpendicular bisector. That's an elementary construction for the midline or perpendicular bisector, and that allows us then to find the point O. And once we have the point O, well, we open our compass, put its center there, choose any one of these points, and draw the circle that will go through all 3 points. And the crucial reason is that any point on the perpendicular bisector, say that one there, is equidistant to both of the points that we started with. This distance equals this distance. Or in rational trigonometry, which is a better way of thinking, this quadrans equals this quadrans. Quadrans being square of distance, which is mathematically more convenient to work with, generally speaking. Alright, so that's Euclid's solution of the PPP case. And note, there's only one solution. These 3 perpendicular bisectors only meet at that point, so there's only one circle that goes through 3 given points in the plane. And perhaps another thing to remark is that there is a condition on the 3 points. If the 3 points happen to lie on a line, happen to be collinear, well then this construction doesn't really work, because then the bisectors are parallel and they don't meet. In that case, there's no proper circle that goes through 3 collinear points. Of course, in that case, there's a line that goes through them, but it's not really a circle. So this is typical of the Apollonius problems. There are special configurations where you might not get a solution, or where the number of solutions might be less than in the generic case. That's an interesting aspect of this Apollonius problem, is what kinds of configurations of the 3 objects give what kinds of solutions. in the other bottom corner of the pyramid of 10 possibilities was the case when we have 3 lines. And this was also solved by Euclid earlier. So the story is here that we have 3 given lines in the plane. For example, this line L, and this line L. And the job is to construct a circle that touches these 3 lines. For example, this circle. It's often called the in circle of this triangle. And Euclid shows how to construct this. The essential construction is that of constructing an angled bisector, or just a bisector, at each of the vertices of this triangle. So let's have a look at, say, this bisector. What is this? This is a line that splits this vertex. So here we have 2 lines meeting at this vertex. And we want to form a third line which lies equally between those 2 lines. In terms of angles, it means that this angle is the same as this angle. In terms of spread, of rational trigonometry, it means that this spread is the same as that spread. So how do you do that? Well, Euclid tells us that what we do is we take our compass and center it here and draw a circle that meets the 2 lines in 2 points. Say those 2 points there. And then we take our compass and center it here and make it go through there. Draw a circle. And then do the same thing with the other point that we found here. Center the compass here and make a circle that goes through here. Those 2 circles that we've constructed both go through this point, but they also meet at some point up here. And if we join that intersection with that intersection, we get this bisector. Now, if you look carefully at that prescription, you will see that there's actually a little bit of choice. Because when we started, we drew a circle centered here, and we cut the 2 lines with this circle. But a circle like this meets a line like this in 2 points, and the same circle meets the other line in 2 points. So when we chose a point on both lines, we chose these 2 points. We could also have chosen these 2 points. Right? Those are also 2 points on the 2 lines from the original circle. And then if we had carried on the construction with a circle centered here through here, and a circle centered here through here, they would have met down here, and we would have gotten the other angle bisector or bisector. The lesson being that there are in fact 2 bisectors of a vertex. This one, and they're in fact perpendicular. The same story here at this vertex of the triangle. There's 1 bisector, and there's the perpendicular bisector. At this vertex, there's 1 bisector, there's the perpendicular bisector. Alright, so then one can pretty easily see that these bisectors will meet. Because this point here where these 3 bisectors meet is then equidistant or equiquadrant to each of the 3 lines that we started with. In other words, it's then the center of the circle that touches the 3 lines. That point is called an incenter of the original triangle. But because there are in fact these other angle bisectors around, there are in fact other points which are playing the same role as this incenter, namely these points here. So here's another point where 3 of these bisector lines meet. And here's another such point, and there's another such point off the page a little bit down that direction where these 3 lines meet. So there are actually 4 incenters. Sometimes these 3 are called excenters, but I like to call them all incenters. And then the circle construction turns out to work not just for this one, but also for the other 3 as well. So we get circles which touch the original 3 lines, centered also at this point, another one centered at this point, there it is there, and another one centered at this point down here, something like this. So in this case, the LLL case has in fact 4 solutions corresponding to these 4 incenters that are obtained with this construction. So this shows that this Apollonius problem is a little bit more subtle than at first it might appear. There are often more than one solution. And in fact, for the big case, where we have 3 circles, there are in general 8 solutions. So there are 8 circles that generally touch 3 given circles in the plane. This problem of Apollonius teaches us about the importance of constructions as well. And it's very interesting to compare our present modern-day approach to mathematical constructions with that of the ancient Greeks or the 17th and 18th century mathematicians, who are much more aligned with the ancient Greek point of view than they are with our modern point of view. So these days, students first of all don't learn very much geometry. Apollonius would be shocked to learn that most math majors who graduate from university with a math degree know almost no geometry. There's only a few theorems that they know that Apollonius did not know. But there would be literally hundreds of things that Apollonius knew that the modern math major does not know anymore. It's remarkable. But another aspect of this is the significance of constructions has dropped off the scene. If you look at Euclid's Elements, which was, of course, the Bible for geometry and mathematics for most of the last 2,000 years, you see that many of the results are framed not in terms so much of theorems, but in terms of constructions. Euclid teaches us how to construct various things, how to construct the incenter, how to construct an equilateral triangle, how to construct various things. And this is an important aspect of learning geometry in the ancient Greek point of view. And this was shared by the European mathematicians in the 17th and 18th century, but it's really dropped dramatically now, so that nowadays young students are almost not familiar at all with explicit constructions. Now the tide is turning, and I'm going to talk a little bit about why, but it's a very interesting thing, and it's important to point out the importance of constructions. There's a general principle underlying this, which we might say is the following, that we should construct first and then discuss. So before you discuss or talk about a mathematical object, it makes sense to construct it first. First you construct something, and now we can say, now let's study various properties of it. The modern approach to mathematics finesses this. So in the modern world, we use these words, particularly the words let, consider, and define, to somehow avoid actually having to construct things. It's a sleight of hand. It's a kind of a grammatical twist that allows you to get away. It's like a get out of jail card. So let me try to illustrate this with an example here. Here's a lemniscate L. It's a classical curve. And here's another cubic curve. Let's call it a folium F. And this is the kind of thing that we say in modern mathematics in the year 2000, roughly. Okay? We say, for example, let A be a point on the lemniscate L. So here's the lemniscate L, and we say, let A be a point on the lemniscate. And in our minds, that conjures up this point A on the lemniscate. The phrase itself is a construction in some sense. It's a grammatical construction which we interpret as a mathematical construction. So suddenly in our minds we say, okay, now we have a point A on the lemniscate. And then we might say, consider the tangent M to L through A. It's a lemniscate. There's a point A on it. There's the tangent to the lemniscate through A. So we can say, consider this tangent. So now we're considering it. We haven't constructed it. We haven't shown how to obtain that line. We're just using this phrase to conjure it up. Now it's there. Now we can start talking about it according to the modern point of view. Then we might say, define B to be the intersection of M and F. There's the tangent M that we've just considered. And now we say define B to be this intersection between this folium and this line M that we've just made. And bingo, there is B for us. You can see it there. There it is. Now a classical geometer, the ancient Greeks, would look at this with extreme suspicion. They would say, wait a minute. How do you construct a point on the lemniscate? What is the lemniscate? How do you define the lemniscate? Surely that has something to do with whether or not you could actually find a point on it. When we say consider the tangent line to L through A, they would certainly object. For them, a line could only be constructed by specifying 2 points on it. That's how you constructed a line. You had one point and another point, and then you drew the line through those 2 points. And if you didn't have 2 points, you didn't have a line. So you might say, well, this is some kind of limit, okay? We take a point here, and then we let C be another point. We draw a secant. We let C approach A, and then we let M be the limiting case. No, no, Euclid would say. And Newton would also say, no, no. Okay? Most classical mathematicians would say this is not a proper construction. You need to construct this tangent by finding an explicit other point on it. And 17th and 18th century mathematicians spent a lot of time on this kind of thing, which is completely now outside of our radar systems. And this insight has been completely lost now in the modern world. Even this third point is sort of interesting. How do you construct a point? Well, according to the ancient Greeks, if you want to construct a point, you need 2 lines that meet at the point, or perhaps you can intersect a line and a circle to get a point. But a line and an arbitrary curve, whether those actually meet, that is a more subtle issue. Okay. So the moral of the story is, I think we tend to overly rely on these words, which are improper replacements for the much more careful notion of constructions. Okay. So it's not bad for us to go back, for young people to be taught yet again the importance of explicit constructions in tightening our mathematics. I'm going to be talking more about this kind of issue in the Math Foundation series. If you're interested in this kind of thing, I will be talking a lot more about that. So in fact, we are now in a period, very interesting period, a great revival of geometry is happening in the modern age. And this has been given a help by a number of things. First of all, we have now these lovely dynamic geometry programs that bring classical geometry and constructions to the computer of anybody who wants to. So Geometer's Sketchpad, well known in America as an educational tool, but also as a tool for research and development that allows you to make classical constructions with points and lines and circles and many other things, and then to move things around and see how various constructions change when you change the inputs. Then there are various variants of that. For example, C.a.R, which is short for compass and ruler. This is a lovely program, essentially a tour de force by René Grothman of the University of Eichstätt. And it's free. Okay, so you can download this program for free, and you can start working on it. It's really highly recommended. GeoGebra will be familiar to some of you. That's also free. Then there's Cabri and Cinderella, and probably a few more too. So these are excellent tools which bring geometry to students, and when you start playing around with these tools, you start to learn the importance of constructions. You can't just tell, in general, a program like this, well, draw a tangent to this curve at this point. You really want to construct a tangent by finding some other point on it. So in general, the importance of constructions comes through to us once we start explicitly working with these dynamic geometry programs. Another important development is this rational trigonometry and universal geometry, which I've been developing. Okay? This gives us a whole new language for talking about the metrical aspects of geometry, a language which is much more akin to the understanding of the ancient Greeks. much more algebraic and less analytic and much more general and powerful technology. And then there's this sort of an increasing demand for visual mathematics, concrete educational materials. People, especially young people, want to see visual things, and they want things to be concrete and not so abstract. So I think YouTube, for example, is an important contributor here. We can now start seeing a lot more things, and when we're interested in seeing, we're interested in geometry. So geometry is coming back, and the importance of this Apollonius construction problem is going to be increasing as an educational tool in the coming century, in my opinion. So if you'd like to have a go at trying to solve some of the construction problems of Apollonius, probably you should learn a little bit about circle geometry. So I'm going to just remind you of some facts. So one of the lively properties of a circle is what I call the subtended spreads theorem, which is that if you have a circle and you have a chord AB on that circle, so 2 points on the circle, and then you look at that chord from different points on the circle, say that point, or that point, or that point there, then that spread is the same as that spread is the same as that spread. So that's called the subtended spreads theorem. And so spreads is the rational trigonometry equivalent to angles. It's not an angle, it's something more fundamental and more natural algebraically. Here's a very quick definition for those of you who know what an inner product or dot product is. So if you have two vectors v and w, and you want to define the spread between them, here's the definition. It's 1 minus this ratio, take the dot product between v and w and square it, and divide by v dot v times w dot w. So those of you familiar with classical trigonometry and so on will recognize that this is the same as the square of the sine of the angle. But this definition involves no inverse cosine or inverse transcendental functions. It involves no square roots. It's purely algebraic. It's a superior formulation of things, in particular because of this theorem you can see. In classical geometry with angles, this is not exactly a proper theorem, because this angle and this angle, they're equal, but they're not equal to this angle. You can see that. This is a bigger angle than this one. However, the spread is better suited because this spread is actually the same as that spread, as it turns out. That's an important result. Another important fact has to do with the other important notion of rational trigonometry, which is just the quadrants. So the quadrants of a vector is just the vector dotted with itself. It's the square of what's usually called the distance. And so here's another important property, that if you have a circle and you have a point, and you draw lines through this point that meet the circle, then there's a certain relation between various products of quadrants. So if you take this quadrant and multiply it by this quadrant, then that's equal to this quadrant times this quadrant. And that doesn't matter where you position this thing. In particular, if it becomes tangential, then the same product is equal to this quadrant squared. So this common number, this product of quadrants that's associated with the point A, is called the power of the point. That's the power of the point A with respect to C. That's an important notion in circle geometry. And then it turns out that if you have two circles like this one and this one, there is a radical axis which is a line which defined by those points whose powers to the two circles are equal. Okay, so those are some important aspects of circle geometry that figure in some of the solutions to Apollonius' problems. Another important thing to know about is the pole-polar duality determined by a circle. So if you have a circle in the plane, the most important property of the circle is the fact that it associates a duality between points and lines. So this point A and this line here in red are dual in a precise sense. And that can be described in a number of ways. The simplest way of seeing it is that if you take the tangents to the circle through this point, so that red dotted line and that red dotted line, then they meet the circle, these 2 points. If you join those 2 points, then you get the polar of the point A. So as A moves closer to the circle, the polar moves close to being a tangent. As A moves further and further away, the polar gets closer and closer to being a diameter. When A is actually infinitely far away, then we get a diameter, and then when it's on this side, then we get lines on this side. There's a better definition of this polarity, which is the following, that if you take 2 lines through A, which meet the circle in, say, 4 points, then those 4 points determine a quadrangle, and we can draw the other lines joining those 4 points in green. And those other lines, those 4 lines, will meet in an additional 2 points. So aside from A, there will also be this new point right here, and there will be another new meet where these 2 things meet somewhere in that direction. And if you join those 2 points, then again you get the polar of A. And that definition has the pleasant property that it also works if A is inside the circle. So there's a lot of remarkable things about this. So in particular, it's remarkable that this whole construction does not depend on the 2 lines through A that you chose. If you change this line a little bit, the 4 points change, but the resulting polar turns out not to change. Okay, there's a related notion here. If we look at this polar line to the point A, and we join A with the center of the circle, giving us that diameter, then the diameter and this polar meet in a new point, call it B. And the relationship between A and B is particularly interesting. So as A gets closer to the circle, B also does, and as A gets further away, B gets closer to the center. And it turns out that the product of this quadrant and this quadrant is always constant. It's always the product of the quadrants of the circle with itself. And this relationship between A and B is called inversion. So A and B are inverse points with respect to the circle C. This is a very important transformation associated to a circle, this inversion that sends points outside to points inside and vice versa. And it has the remarkable properties that if I take a little circle and invert all the points on that circle, then I'm going to get another circle. I don't get some weird curve like an ellipse or something even stranger. No, I get the inverse of a circle is itself a circle. That has to be qualified a little bit. If the circle happens to go through the center, for example, if we chose that circle there, then its inverse is not a circle exactly, but it's a line. So if we group lines and circles together, then we can say that inversion takes circles or lines to circles or lines. And then it turns out to also preserve spread. So if we have 2 lines which meet at a spread S and we invert them both, then we might get 2 circles, or we might get 2 lines. Then those 2 circles or 2 lines that we get when we invert, they meet tangentially with the same spread as the original ones did. Okay, so these are aspects of circle geometry that you probably want to become familiar with if you're going to have a serious go at the Apollonius problems. So really important mathematical problems have consequences. They are usually related to a lot of different mathematics, and they have applications, varied and interesting. And this is a real test of, ultimately, the importance of a famous mathematical problem. So from this point of view, the Collatz problem has to be admitted is a relatively unimportant problem. Very interesting, but relatively unimportant. However, this Apollonius problem is exceedingly important. It has a lot of connections with other things, and it has actual applications, even to real world today. One example is the natural connection of the Apollonius problem to the hyperbolic trilateration problem, introduced by Newton. This is a problem where you have maybe a ship at sea. You want to determine its position, and if you know the differences in distances from 3 fixed points, then you can hope to figure out where your ship is. This has a 3-dimensional generalization, which is important in global positioning systems. There's a special case of the Apollonian problem called the Apollonian gasket, which is naturally connected to what's called fractals. In fact, it was one of the first examples of a fractal. So a particular situation is when you have our 3 circles, say in black here, which are themselves tangent. Okay, not 3 general circles, but 3 special circles which are themselves tangent. This is a very interesting and beautiful situation which has generated a lot of study. It's connected to hyperbolic geometry in a very profound way, to group theory, and there's a lovely metrical relation between the various radii of circles involved here that goes back to Descartes and has been rediscovered by quite a few people since. So once we have 3 touching circles, then it turns out there are only 2 solutions to Apollonius's problem. There are 2 circles which are tangent to those 3 circles. One of them is the big blue one, and the other one is this small blue one inside here. Well, you could also say, in fact, there's 5. Yes, because this circle here is itself a sort of a solution, right? The circle is tangent to itself, and it's also tangent to the other 2. So you could also say that there's, in fact, 5 solutions, but really there are 2 more solutions. Now, the beautiful thing is then we can iterate this. So we can say, all right, then suppose we look at this circle, and the big blue circle. Then we can find 2 circles which are tangent to them. One of them is this other black one, which we already have, but the other one is a new one, that green one there. And so we can create more circles which are tangent to the given ones. We can create another one there, another one there. We get a whole family of smaller and smaller circles forming this gasket-like infinite pattern. Okay, so Apollonius' problem, very interesting, very important, and the beautiful thing is that you can work on it. So you could get Geometer Sketchpad or C.a.R, which you can download for free. So you can basically do these constructions on your computer, and you can start to try to work your way up Apollonius's pyramid by trying what happens when you have 2 points on a line, or 1 point and 2 lines, and see if you can figure out how to actually construct a circle which goes through the 2 points and is tangent to the line, for example. All right. Once you figure that out, then you can throw in a circle and see if you can move towards the 3 circles. That's a very big challenge and will very well take you years, perhaps, of steady work to get to that. If you get frustrated, you can always look up the solution. There's many places on the internet where you can find solutions to these famous problems. But it's challenging to work on it yourselves. In our next lecture, we're going to switch gears and do a little bit of graph theory. We're going to look at a lovely problem in graph theory called the graceful tree conjecture. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.